Buongiorno a tutti, sono Paola Goria, il Mediterranean District Manager per Regenesis. Oggi sono qui per introdurvi un webinar un po' particolare rispetto a quelli che facciamo di solito, perché non è un webinar tenuto da noi in italiano, ma oggi proponiamo la registrazione di un altro webinar che abbiamo fatto poco tempo fa, relativo a un intervento molto particolare che è stato realizzato da Regenesis in collaborazione con la società De Conta della Repubblica Ceca su una contaminazione molto importante causata da un incidente, quindi uno spill di benzene puro. Vi racconterò poi tra poco di che cosa si tratta. Come detto, la presentazione sarà quindi tenuta da altre persone, non da noi, sarà in inglese. A parte questa breve introduzione ci sarà poi la parte delle domande e risposte che sarà invece live e in italiano, quindi come sempre vi esorto a mandare le vostre domande in chat perché le raccoglieremo e io poi al termine della presentazione cercherò di rispondere a quanto più possibile e come sempre poi vi risponderemo eventualmente via mail a quello che non abbiamo potuto trattare. Vi faccio una brevissima presentazione dei due relatori. Jack Shore è il nostro Regional Manager Regenesis e Andrei Litovsky è un tecnico di grandissima esperienza della società De Conta. De Conta è una società che lavora da oltre 30 anni nel campo delle bonifiche, si occupa sia di caratterizzazione che di realizzazione di interventi, è una di quelle società che lavora un po' su tutto il procedimento, quindi sia per la parte di progettazione e consulenza, sia per la realizzazione vera e propria delle attività. Quindi fornisce normalmente degli interventi chiavi in mano. Lavora principalmente, appunto, come dicevo, in Repubblica Ceca e in Est Europa, quindi sia a livello nazionale sia a livello internazionale, e uno dei suoi focus principali è proprio quello di cercare di lavorare con tecnologie innovative e utilizzare il più possibile quello che il mercato propone. Ondrej in particolare è il responsabile del loro dipartimento di ricerca e sviluppo, oltre ad essere un tecnico con esperienza quindicennale, e proprio grazie a questo suo focus sulla ricerca e sviluppo, in questa situazione particolare in cui era necessario intervenire in modi molto rapidi e flessibili, è venuto proprio a cercare, a parlare con noi per utilizzare una tecnologia che non è proprio la classica tecnologia che viene usata negli interventi messi in sicurezza. Vedrete poi nella presentazione appunto come ci si sia focalizzati anche su tecniche di rilevamento e di verifica in continuo che sono stati degli strumenti molto importanti. Jack Shore, il mio collega, è il Regional Manager per Regenesis Europa. Anche lui, nonostante sia una persona giovane, ha un'esperienza ormai quindicennale nel campo delle bonifiche, ha lavorato come consulente, come contractor. In Regenesis ha coperto, credo, qualsiasi ruolo si possa pensare, dal tecnico di campo al technical service, quindi lo specialista che si occupa dei dimensionamenti, al commerciale. Ha visto passare sotto le sue mani oltre 3.500 siti in tutta Europa ed è una persona che ha sicuramente come grande qualità una flessibilità mentale enorme, e questo sia per le sue capacità che anche capacità, direi, di noi tecnici di Regenesis, ci ha proprio portato a poter lavorare su questo progetto particolare e estremamente importante. Vi faccio solo un piccolissimo accenno a questioni operative, soprattutto legate all'audio. Se doveste avere problemi di audio, vi consigliamo di disconnettervi e riconnettervi utilizzando lo stesso link che avete usato adesso per entrare nella riunione, perché normalmente questo risolve. Un'altra cosa che consiglio è quella di chiudere tutte le applicazioni che utilizzano banda, in modo da avere più banda possibile a disposizione per vedere il webinar, e tendenzialmente non dovrebbero esserci problemi particolari. Ricordo di nuovo di mandarci le vostre domande, così poi potremo rispondere. Tornando al caso, ecco, è un caso particolare, un sito di cui noi siamo orgogliosi, un progetto importante, non solo perché è stato un lavoro vasto, quindi di entità importante, ma per come è nato, nel senso che questo è stato probabilmente uno dei peggiori incidenti avvenuti in Europa negli ultimi anni, con uno spill di benzene intendo benzene, non benzina, quindi non una miscela, enorme, che ha creato un possibile danno ambientale estremamente importante, e noi siamo stati contattati ancora in fase di messa in sicurezza, quindi a differenza di quello che succede normalmente quando si fanno interventi in situ, in questo caso noi siamo intervenuti proprio ancora nella fase di messa in sicurezza che ovviamente è stato un processo in itinere, non abbiamo potuto fare uno studio approfondito, una valutazione dettagliata di tutti quelli che potevano essere gli scenari, perché era proprio una corsa contro il tempo. Abbiamo dovuto intervenire in tempi molto rapidi, adattando il nostro dimensionamento e il nostro intervento a tutte le varie nuove evidenze che emergevano e alle modifiche che De Conta stava facendo proprio alla strategia. Se pensate, vedrete nella presentazione che poi l'intervento reale è consistito in una cinturazione del sito con delle palancole e un'applicazione del PetroFix a valle di questo palancolato, ma la definizione di questo palancolato ha avuto non so quante versioni diverse. Si è ipotizzata prima una barriera sola valle, poi una barriera valle con delle ali, poi una barriera piccola con delle parti reattive, e per ognuna di queste ovviamente dovevano essere valutati i pro e i contro, gli interventi associati, il fatto per esempio che facendo una barriera solo a valle risultassero quantità enormi di acqua da gestire per evitare che poi ci fosse un bypass, quindi tutta una serie di aspetti estremamente complicati sia tecnici che operativi, ma che sono stati analizzati e risolti in tempo reale. Quindi è sicuramente un intervento molto interessante da questo punto di vista, oltre, ripeto, per l'entità stessa della problematica. Non mi dilungherò più, lascio la parola a Andre e Jack per la presentazione e vi aspetto poi per la parte delle questions and answer. Grazie a tutti.
It was a big spill that happened in Czechia. It happened actually in February 2025 when a train that was carrying pure benzene from the manufacturing site derailed, and it caught fire. Basically 14 out of 17 wagons that were carrying benzene were severely damaged, and the benzene that was in the wagons spilled into the environment. The estimate is that about 400 tons of benzene were released, while about 200 to 300 tons got infiltrated into the groundwater. This incident was actually the biggest benzene incident ever recorded in Europe, and as benzene migrated very quickly into the subsurface and into the groundwater, we've seen very early impacts of benzene in surroundings. Benzene was detected in the nearby lake about 100 meters from the incident site already a few days after the incident. So this underground migration was extremely fast, and there was very significant risk both to human health and environment. And that's why the Conta company was called to the side by the authorities, as we are the only company in Czechia that combines both the emergency response and site remediation services. On this picture on the right side, you can see the aerial view of the site where you still have the incident site, and you can see benzene L-nipple that was observed on the lake surface very few days after the incident. We were contacted by the authorities. We came to the site, and it was a complete mess. There were still a lot of works going on the incident site. The wagons were still present, and they were taken care of by the National Fire Service, and we knew that benzene was migrating towards the lake, so we need to collect as much information as was possible. Of course, there were very high safety risks due to benzene presence. Benzene is, of course, very toxic. It's actually carcinogenic, and its vapors are highly flammable, and there is also high risk of explosion. So the early days on the site were very hectic, and we had to use all the protecting equipment that can be used in such cases. In addition to that, the situation was evolving very quickly, so we needed to assess the situation and to get all the information possible as soon as possible. And we decided to do that via excavation and installation of this like combined survey and pumping pits throughout the site to see if there is free benzene L-nipple floating on the groundwater. Of course, we also started installing monitoring wells, and we already started also with installation of some recovery wells. The main finding we had after several weeks was this estimation that there is about 200 to 300 tons of benzene present floating on the groundwater in form of L-nipple. And we informed the authorities about this. And later on, the state claimed so-called state of emergency, and this helped rapid remediation of the site. As Jack mentioned, this was not a typical oil spill. The properties of pure benzene are, of course, different compared to normal oil. It's highly volatile, toxic, and explosive, as I mentioned. So there were very high risks for the site personnel, and it has also very high mobility in the subsurface. Its absorption on the soil materials is relatively low, and it has very low viscosity. And speaking about organic solvent, it has relatively high solubility, so it was rapidly partitioning into the groundwater. In addition to that, the site conditions were very favorable for a very quick mobilization or flow of the of the benzene in the subsurface, as the site was actually a former gravel pit with very highly permeable gravel aquifers. And it had minimal attenuation capacity, and there was direct hydraulic connection to adjacent lake. So this quick increase or quick migration of benzene into the lake resulted into quick increase of benzene concentrations in this lake, and about 25 days after the incident, we've seen a mean benzene concentration in the lake around 450 micrograms per liter. Just to explain you how this could have happened, here is a short presentation of our benzene migration conceptual model. On the left hand, you can see the geology of the site. We have like about 1.5 meters of loam, and then we have about 6 meters of gravels that are partially saturated, and then we have a clay insulator. And what happened when benzene was infiltrating, we had huge benzene lagoons close to these wagons, and this benzene was rapidly migrating downwards, not only because of its gravity, but also because of elevated heat caused by the fire and firefighting water and surfactants that were sprayed over these lagoons, and they were basically pushing benzene L-level downwards. Then when benzene reached the groundwater level, it accumulated there and it created L-level, and a part of this L-level was dissolving into the groundwater, but it's also floating along the groundwater table downwards, and it was soluting into the groundwater also along the way. So it was spreading very quickly towards the lake, mainly in form of L-level, but also in form of solution in groundwater. The groundwater migration towards the lake is also quite significant, but it's not that quick as was the migration of pure L-level on the water table. And when this benzene got into the lake, it got soluted in there. We estimated that the maximal concentration of benzene in the lake, if there was no intervention, would go up to about 65 milligrams per liter of benzene in a lake, while already about 4 milligrams per liter are lethal to fish. And the spreading, as I mentioned, was very quick. We've seen benzene in a lake that is like 100 meters far in very few days. And then this lake is connected to another lake and then to a river ecosystem, and there would be quite significant downstream impacts on these as well. The estimated mass flux of benzene at the beginning of the remediation was about 400 kilograms per day, and the secondary source migration was around 23 kilograms per day. And then we would have migration of about 4 kilograms per day to the downstream area. We presented this uncontrolled migration scenario to the authorities. We warned them that the surface water in this first lake can increase up to 65 milligrams per liter, which would cause actually acute toxicity not only to the lake environment, but it would be also toxic in the surroundings, as benzene will evaporate from the lake and there will be toxic vapors all around. And it was clear that even the downstream lakes will have very high benzene concentrations and will become toxic. And there was a potential to also the benzene will also migrate into the nearby river and then farther downstream to other lakes that are used for recreational areas. So the risks were very high, and there was another huge risk that there will be floods coming, and this flood risk would cause large scale redistribution of all the benzene that was present downstream, with potentially very disastrous results. So it was decided that there is immediate containment necessary to stop the migration of benzene downwards. And we decided that we will install a sheet pile wall on the site to prevent the downstream migration. This sheet pile wall installation was started already in March, and it was finished after 43 days after the incident. It was extremely quick. The sheet piles were taken to the site from all around Europe, and the sheet pile wall was installed in order to contain the majority of the benzene contamination present on the site. After this sheet pile wall was installed, so-called controlled area was established inside, and we had a first time or for the first time, we were able to rest for a while, as the biggest risks were captured inside this controlled area. As there were two parties working against one another, the connection you can see on the right upper picture wasn't perfect. It looks a bit like this. It wasn't perfect, but it worked. So that was the main goal. And this sheet pile wall length was about 700 meters, and the enclosed area was around 28,000 square meters. The groundwater volume inside this controlled area was around 25 to 32 cubic meters, and we knew that the hydraulic system inside was effectively isolated from the surrounding groundwaters. We also knew that there were different groundwater levels outside and inside the sheet piles, so the performance of the sheet piles was verified, and we confirmed that the sheet piles worked as a containment for the benzene L-nipple, although they don't seal like 100%. There is still some groundwater migrating through the sheet piles. The L-nipple migration was basically stopped thanks to the sheet pile installation. Yeah, so concerning the mass balance that we did after the sheet pile wall installation, we've estimated that we had about 200 to 400 tons of benzene captured in the controlled area. And this means that about 96% of benzene that was released was contained inside this controlled area. When we have looked on the distribution of the contamination, a majority of it was present in form of L-methyl that was gradually dissolving into the groundwater. Only about 10% was present dissolved in the groundwater at the time, and we had 10 to 15% retained in the soils. When we calculated the mass that reached the lake, it was estimated to about 600 kilograms to 1.3 ton, and thanks to water spraying that was performed by the State Firemen's Brigade, the concentrations of benzene in the lake dropped down very quickly, and we didn't see any significant toxic impacts on the lake ecosystem at all. In addition to that, we knew that there were about 2 to 4 tons of benzene that migrated downwards from the controlled area earlier before the sheet pile wall was installed. And although the further migration was limited thanks to so-called hydraulic shadow effect of the sheet piles that was basically shading the groundwater down gradient, and therefore the groundwater migration is way slower. It was still a very high risk, and we knew we have to investigate this issue further. We were also asked by the authorities to prepare so-called emergency remediation strategy, basically a document that will guide us through the remediation. We developed it very quickly, within about 7 days. At the beginning, it was intended to last for 6 months, but now the remediation was extended to 20 months, and there will be follow-up remediation projects prepared later on. The key objectives of this emergency remediation strategy were mainly, of course, containment of the benzene and effective benzene removal from the groundwater and from and mainly the benzene that was floating in form of L-methyl on the groundwater, but also it was important to rapidly restore the railway and to investigate and monitor the site in detail. And we also wanted to minimize both the environmental and financial risks and optimize the remediation efficiency. The approach of the remediation in the control area was quite straightforward. We were recovering the L-methyl by pumping and skimming in the initial phase, and then we contained the contamination, and we were pumping the groundwater with the dissolved benzene, and we cleaned it on granulated activated carbon units that we installed on site. And in case of the areas outside of the control area, we've decided to combine L-methyl recovery in cases there was L-methyl present, and groundwater extraction and in situ technologies. And we tried to focus on adaptive site management. We propose that we will think about different technologies that can be used on a site based on the evolving conditions of the site, and that we will validate these through laboratory and pilot testing, and then we will scale it up to the full operation. So first thing I will touch briefly was soil containment and the railway restoration. Basically, what we found was that luckily the soil layer that was highly contaminated beneath the railway was relatively narrow, and the amount of the soil that needed to be excavated was relatively small. So what we did was that we basically removed this contaminated soil to the site, and where the soils were highly contaminated, where these lagoons with benzene were present earlier, and we covered these contaminated soils with bentonite, and we left it on the site. This provided space to the companies that were restoring the railway, and they were able to restore the railway operations rapidly. So the first trains resumed service after 107 days after the incident. Concerning the LNAPL recovery and pumping, we were directly pumping the benzene from our excavation pits and later our recovery wells, and we were combining the pumping with skimming to enhance the amount of recovered LNAPL, and we transported the recovered benzene to the producer facility where the benzene was produced originally. It's actually only 10 kilometers far away, so it was quite convenient for us to transport it there. There were, of course, a lot of operational challenges, as the benzene LNAPL created emulsions with the groundwaters, so sort of milk-like looking liquid, and there were high safety risks during the handling and disposal of the benzene, of course. But within about a month, we were able to pump out majority of LNAPL that was present on the site, and to remove about 100 tons of LNAPL, and the rest of the LNAPL was quite quickly dissolving into the groundwater, and it was not really possible to pump it out anymore. Concerning the pump and treat system that was installed on the site, there were about 70 extraction wells installed in the controlled area, and they were used periodically to pump the groundwater with dissolved benzene out, and this water with very high benzene concentrations was treated on high capacity granulated activated carbon filters. We had 3 filters on the site, or we actually still had them there. Each unit contains about 20 cubic meters of activated carbon, which is about 10 tons. And we are always pumping the highly contaminated groundwaters through the first filter, so-called high load filter. Then we polish the groundwater in the second filter, that is installed in a series after the first filter, and then the last filter is on standby. It's actually empty, and every time our high load filter gets fully saturated by benzene, there is a car coming that brings a new, fresh, reactivated, granulated activated carbon. This carbon is injected into this standby filter, and the contaminated activated carbon is pumped out from the high load filter, and it's taken to Austria for reactivation, and we can continue pumping. The performance of these filters is quite outstanding. The sorption capacity of the granulated activating carbon is about 20%. So on each 10 tons of carbon, we are able to separate about 2 tons of benzene. We were thinking about some pretreatment strategies, but we found out it was not necessary, and the efficiency in terms of reducing benzene concentrations is basically 100%, as the treated water does not contain any measurable benzene, and we were able to safely re-inject it into the aquifer or into the adjacent lake. At the moment, we already removed about 56 tons of benzene this way, and the influent concentrations were reduced from about 1.5 grams per liter that were present in the groundwater at the beginning to about 400 milligrams per liter. And we treated about 85,000 cubic meters of groundwater already. So the key advantages of the system is this high operational safety, also rapid deployment. It's a proven technology, and it's very cost effective at long term. And this brings me to remediation beyond the controlled area. As I mentioned, about 96% of benzene was contained, but remaining 4% equals to about 8 tons. And these 8 tons migrated beyond the barrier, and it required rapid migration control and targeted remediation. We prepared a remediation concept based on a rapid in situ sorption using PetroFix, as we were aware of this technology, and we wanted to follow up with in situ chemical oxidation and biodegradation. The workflow of the technology selection and implementation was based on lab scale testing, then pilot testing, and then a full-scale application and optimization. In case of PetroFix, we skipped the lab scale testing, as I will mention later, but in case of in situ chemical oxidation and biodegradation, we did also lab tests as well. What we didn't know earlier was that there was some contamination present also on the east area of the controlled area, as the former gravel extraction area was bigger than the current lake, and the gravel was excavated in these areas as well, and then it was backfilled with low permeability loams, and this resulted in eastward migration of benzene also this way. So we were also asked to rapidly react to this situation and to extend the sorption barriers we installed. And this brings me to Jack.
No problem at all. Let's just share my screen and get the presentation up, and we can get started. So thank you for the handover. So this part of the talk, I'm just going to introduce PetroFix within the concept of how it was used on this particular project. One of the reasons why we were so keen to tell this story is because what was happening here is a rapid response to a sudden loss of benzene, where the Consa were essentially deploying a integrated remediation treatment strategy. So starting with physical removal and capping, and then firm hydraulic control combined with pump and treat. And then as different parts of the site required different technologies to essentially stop the spreading and reduce the risk posed by this spill, this is where colloidal activated carbon, of which PetroFix falls under that umbrella, came into the wider remediation strategy. So the part of the talk I'm going to do is just introduce you to this concept of colloidal activated carbon, the product PetroFix, and then how it works in the subsurface once it's been applied. So colloidal activated carbon is typically applied through direct push injection, or you can inject it into fixed injection wells as well. So I'll start off with what is a colloid. So a colloid can be defined as a substance composed of two homogeneous phases, one of which is dispersed in the other. So colloids usually provide a surface with a high cation exchange capacity that also exhibit instability in soil chemistry. So there's three types of mixtures that fall under the umbrella of a colloid. So there's three types of mixtures. One is a solution, one is a colloid, and one is a suspension. Okay. The size of the dispersed phase for a colloid can be between 1 to 100 nanometers. Particles are often invisible to the naked eye and will only settle upon centrifugation, and these particles diffuse slowly. Now, within our lives, we come across colloids all the time. So ink is a colloid, milk is a colloid, paint is a colloidal suspension, as is wine as well. So if you're thinking of colloidal activated carbon, it's something that looks very much like ink. It's something that looks very much like black coffee. So why are they useful for in situ remediation? So what we're doing with colloidal suspensions is essentially turning a solid into a liquid, which is really useful if you're looking to inject something in the subsurface. You want something that's going to really distribute well in the subsurface. So we take a solid ingredient, and for our colloidal activated carbon range, we grind that down to 2 microns. So 2 microns is about the width of a red blood cell. So it's smaller than a pore throat in sand or silt. That isn't the end though, because what you do not want to do is you do not want these colloids to agglomerate. You don't want them all to stick together to clog up those pore throats. So we add a proprietary dispersing agent. So this ensures product consistency for storing and application. In this case, we manufacture all of this in the US. We have warehouses across Europe. And then when we're shipping it to Chechnya, then we want to make sure that it's stable during transport and also stable during storage on site. These proprietary agents also make it very easy to handle. Handleability in the field is important, as is mixing, and ultimately they enhance distribution. So this proprietary dispersion agent coats these activated carbon particles that are 2 microns across in this dispersion agent that gives them all a slight negative charge, so that they repel each other, but they then stick to the aquifer matrix. You can then mix it with water, and then it's delivered as a stable liquid suspension. So they're useful when it comes to in situ remediation, because when you're looking at different compounds that you might want to inject into the ground, I always think these are the 4 things you need to be considering. First of all, you need something that's going to distribute really well. We don't want to have a really dense injection grid. We want something that's going to distribute well, where it can make contact with the contaminant, where it can have the desired effect. So you want something that's going to distribute widely in the subsurface. You then want it to be persistent. So you need it to not wash out. You need it to stay where you've injected it, but then it also has to be appropriately reactive as well. And then finally, it's got to be easy to use. You know, for anybody that spent time in the field, ease of use on site is really important. And I also think ease of use and safety in the field is also important. So you want something that's safe and easy to use. So in Regenesis, we have a range of different colloidal technologies. So we have plume stop and PetroFix. PetroFix is what I'm going to be talking about as part of this presentation. They fall under the umbrella of colloidal activated carbon. We also have other colloidal technologies. So we have a colloidal zero valent ion technology called S-micro-ZVI for in situ chemical reduction applications. And we also have a colloidal electron donor as well called Aquafix that continues to release hydrogen for up to 10 years in the subsurface. All of these are colloids. Two of our products, plume stop, PetroFix, they are colloidal activated carbon. We're going to focus on PetroFix because it was used on this site and it's used to treat petroleum hydrocarbons in the subsurface, where typically PetroFix is used for in situ absorption and anaerobic biological degradation. In the case that Andre is discussing today, they actually went down the aerobic route with benzene. In terms of what PetroFix is, so what PetroFix is, it's a colloidal activated carbon or a liquid activated carbon product that is safe to use and very straightforward to use on site. So as I said, we've milled granular activated carbon down to 1 to 2 microns, coated it in a dispersion agent so that when you inject it into the subsurface, it distributes really widely. It's a very adaptable product. So in this case, it was used as in a barrier application. Sometimes it's used to treat sources. In other times, it's used down service runs to stop offsite migration. It provides really fast results. So it's used quite frequently in the spill response industry to stop the spread and reduce the risk of continued migration of contamination. And typically it's applied on sites where your hydrocarbon concentrations are at or near solubility limits, okay? What it can't do is it can't stop surface migration. So this isn't like a boom that you can just spray this on the ground and stop surface migration. And it also cannot stop free phase either. And this is why, as Andre was talking you through this remediation strategy, that where you do have free phase, some sort of pump and treat, some sort of excavation, some sort of stabilization is much more appropriate than using this technology. But it is a non-hazardous substance. So it's a very safe product to use in the environment. It's essentially made of the same stuff that's in your water filters at home. But we're not just using activated carbon to absorb and fix contamination. We can also use it to enhance biological degradation as well. So there's lots of, PetroFix and plume stop have been out now for over a decade. And there's lots of instances that show how colloidal activated carbon, which are commonly paired with electron donors or acceptors, depending on what you're treating, can accelerate biological degradation. Essentially, that we hypothesize that biostimulated bacteria, they form these biofilms that coat the colloidal activated carbon, enabling close contact between that absorbed contamination and the contaminant that they are looking to break down. And there's multiple studies that highlight this. We have probably hundreds of case studies that we can draw on, looking at not only petroleum hydrocarbons, but chlorinated solvents that show when you treat sites with colloidal activated carbon, pair it with an electron donor or acceptor, or rely on ambient electron donors or acceptors, you get enhanced biological degradation. So essentially, there's a 3-step remediation process. The first is absorption. So you inject the colloidal activated carbon into the subsurface, and you're looking to paint the subsurface with a 2-micron layer of activated carbon. So we're coating all of those the sand grains and silts with this 2-micron layer of activated carbon. What that does, it will rapidly remove dissolved phase contamination from the groundwater and absorb it onto the soils. Also, what can be important, particularly if you have low targets that you're looking to hit, is it will also coat your immobile porosity as well. So that problem of back diffusion from your immobile porosity is mitigated against because we've coated it with a 2-micron layer of activated carbon to mitigate against that back diffusion as well. Essentially, then what's going on is we've coated those sand grains with this 2-micron layer of activated carbon. In some cases, as was the case that we're talking about here, we can rely on natural electron acceptors to stimulate biological degradation. But in other cases, we can also pair it with an oxygen releasing compound, so something that we have called ORC, to promote aerobic biological degradation. Or PetroFix also comes with a blend of sulfates and nitrates to accelerate anaerobic degradation of petroleum hydrocarbons in situ. So what happens when you then have this biological degradation? You then have this 2-step process of regeneration of these sorption sites. So this petroleum degrading bacteria is stimulated, and then it starts to break down that absorbed petroleum hydrocarbon mass that leads to the regeneration of these sorption sites. That then cleans off those sorption sites. That then allows more contamination to be absorbed onto the PetroFix, and then it can be degraded. So in some cases, you can create this self-cleaning filter that can be stimulated either through aerobic or anaerobic bioremediation to regenerate those sorption sites, so that then further contamination can be absorbed onto the PetroFix and treated. PetroFix, as I say, coats these flux zones with a micrometer thick layer that then absorb contamination. That contaminant flux then advects or back from advection or back diffusion is then captured. And then in the cases where we are adding sulfates and nitrates, we can kickstart that anaerobic biological degradation, or we can, as we did on this site, work with the existing conditions to promote aerobic biological degradation. This biodegradation can lead to multi-year longevity of this particular product. So it's this case of a single injection, and then you allow this system to play out for many years. You get long-term regeneration. So depending on if you go down the anaerobic route or aerobic route, you can kickstart syntrophic biological degradation, which is a process by which different microbes essentially feed with each other. So you'll have one set that break down, say, BTEX into hydrogen and acetate. What you don't want to do is to have these waste products start to build up to make conditions less thermodynamically favorable in the subsurface for TPH degradation. So another group of microbes can then come along, break those waste products down to keep conditions thermodynamically favorable for petroleum hydrocarbon and BTEX degradation. So this maintains real long-term effectiveness. We have plenty of case studies on this. This isn't from this particular site, but during the development of this project, we have lots of case studies looking at what happens as the nitrates and sulfates and other electron acceptors return back to baseline, and then the impact that it then has on microbial consortia in the subsurface. So we've papers on that. If you'd like to reach out to us in the Q&A section for papers on syntrophic biological degradation, I can absolutely forward those on to you. Otherwise, I'm going to hand back over to Andre now to finish off talking about the site. What I will say, just before I hand back over to Andre, do keep putting your questions in the Q&A section. I'm slowly collating them, and hopefully we will get to them at the end of this presentation. So just bear with me whilst I stop sharing screens, and I will hand back over to Andre.
Brilliant. Thanks a lot for this introduction of PetroFix. I will just briefly touch the pilot tests we did with it. It was very quick, actually, as we were aware of regenesis, and we selected PetroFix mainly because of its readily availability in Europe. And we knew that a high benzene mass can be sorbed on it. It had a proven performance, and there were quite a lot of results from comparable large-scale projects. And from our experience, we also know that regenesis is capable of providing strong technical support. So we selected PetroFix for pilot test. This pilot test basically served as proof of concept. We designed it together with Regenesis, and after 1 month, we had clear results showing that PetroFix is an effective and scalable solution for controlling benzene migration in Hustopeče site. And we started full-scale barrier installation. In total, we injected about 49 tons of PetroFix at the end. The average amount of PetroFix per 1 cubic meter of aquifer was about 7.3 kilograms, and the total barrier length is about 680 meters. So it's a very long barrier that was installed down gradient of these sheet piles along a peninsula that is inside of this lake that is the main acceptor of benzene, and then also on the eastern part of the site. We also had to inject so-called parking agent as the permeability of the aquifer is very high, and we don't want the PetroFix to migrate too far from our injection wells. So we used calcium solution to keep PetroFix close to the injection wells, and on average we injected about 2 cubic meters of PetroFix suspension per 1 injection wells. What I didn't mention earlier was that in this case we decided to inject PetroFix via lines of small diameter wells that targets the full gravel aquifer thickness. The barriers were installed in sequence. We started injections in August 2025 on the peninsula. Then we went to down gradient areas of the sheet pile wall in September and November, and then we injected 2 smaller barriers. You can see on the right-hand picture in February 2026. This was mainly because we found out that there was contamination spreading also in this eastern area, and actually PetroFix injection was required by the authorities that had a good experience with the migration control that it provided on the peninsula. Something about the performance. We've seen rapid decrease in benzene concentrations on the peninsula after PetroFix injections. You can see on a graph the results in the upgradient wells that were upgradient to the sorption barrier. Throughout the time, we had quite significant decrease, but in case of the wells that were actually within the barrier, the decrease was way more obvious. You can see that we started at concentrations around 32 milligrams per liter, and we ended in February at concentrations around 490 micrograms per liter. And more importantly, in case of the down gradient wells that are basically connected to the water of the lake, we've seen a significant decrease from concentrations around 5 milligrams per liter to concentrations around 350 micrograms per liter. So we conclude that PetroFix application effectively halted benzene migration on the peninsula, and benzene concentrations so consistent downward trend, and we did not see any significant increases in benzene concentrations in the lake. We also seen very positive results of the PetroFix barrier installation in the eastern area of the site, where benzene concentrations on average dropped from about 18 milligrams per liter to 4 milligrams per liter in several months. And nowadays, follow-up in situ chemical oxidation applications using Fenton's reagents and enhanced aerobic biodegradation are actually taking place and complement the PetroFix barriers that were installed there. This brings me to key takeaways. For us, definitely this comprehensive site evaluation and identification of the male mobile contaminant mass were crucial for prioritizing remediation strategies with authorities and making effective technical decisions. This early stage L-metal recovery proved highly efficient in reducing the contaminant mass, and the rapid installation of the sheet pile wall was definitely a key measure that provided valuable time for follow-up remediation. Of course, PetroFix injections successfully controlled benzene that bypassed the sheet pile containment and prevented the migration toward the lake. And these granulated activated carbon filtration units also provided a safe and highly effective solution for groundwater treatment. In our opinion, the use of readily available and proven technologies like PetroFix and granulated activated carbon filters can be strongly recommended in similar cases where a rapid response is essential. Although the initial costs at the beginning of the remediation were quite high, the targeted remediation of L-metal and high concentration zones proved far more efficient than treating a large diluted plume that would result in high risks and low effective remediation. In addition to all these works we were doing on the site, there was also real-time air monitoring in the nearby village that confirmed there were no impact on the ambient air quality, and also comprehensive environmental monitoring of drinking water and crops, and so proved that there were no risks and no benzene was present in these materials. And the clear proof of our success of the emergency response is that there is this fishing competition held on the nearby lake, and fish health was protected, and as well as the environment of the lake. To conclude the takeaways, I think adaptive site management was critical for selecting the appropriate remediation technologies under rapidly evolving site conditions. The laboratory and pilot testing proved highly beneficial, and to date we already removed about 155 tons of benzene, and of course we are looking on a significant and sustained decrease in groundwater benzene concentrations. The railway operation was restored within 107 days, and the lake environment and downstream ecosystems were effectively protected. So, in my opinion, rapid response and targeted remediation made the difference, and we were able to mitigate the impacts of the incident as much as it was possible. That's all from me. I don't know if we do have some time for for questions or if we run out of time.
Eccoci di nuovo qui. Spero che la presentazione vi sia piaciuta. Io l'ho trovata molto interessante. Sono arrivate moltissime domande, quindi come sempre risponderò solo a qualcuna di queste e poi ci metteremo in contatto direttamente con voi tramite me, Jack, Andre, vediamo a seconda della domanda specifica come rispondere. Leggo qui un po' di domande, quindi ne scelgo solo qualcuna. Allora, sono arrivate un paio di domande sulla possibile presenza di PFAS in questo sito. Questo perché? Perché sono state utilizzate delle schiume antincendio. In realtà molta parte della, diciamo dello spegnimento dell'incendio è stata fatta con l'acqua del lago, però sono state usate anche delle schiume. Che ci siano o non ci siano i PFAS in realtà è un qualcosa che non sappiamo ancora e non era stato valutato nel dettaglio, soprattutto tenendo conto delle tempistiche dell'emergenza. È possibile che ci siano, sappiamo tutti che ci sono delle schiume antincendio che contengono i PFAS, quindi è possibile che si sia creato un problema del genere. E il fatto che il PetroFix, che è un prodotto a base di carbone attivo colloidale, possa essere efficace anche nell'assorbimento, quindi nel trattamento di una contaminazione da PFAS, è stato uno dei motivi per cui comunque anche in fase di valutazione delle possibili tecnologie è stata scelta questa opzione, perché nel caso in cui ci fossero i PFAS, anche se l'intervento non è stato dimensionato pensando ad una contaminazione da PFAS, quindi l'intervento è stato dimensionato in un altro modo, nel caso in cui ci fossero anche i PFAS, comunque il PetroFix che è stato usato può essere efficace anche su questa contaminazione, quindi sicuramente è un aspetto importante. C'è poi una domanda che chiede: il carbone attivo iniettato viene poi estratto? No, il carbone attivo iniettato si fissa al suolo, rimane all'interno del sottosuolo e viene poi rigenerato nel tempo grazie alla degradazione degli idrocarburi, o meglio scusate del benzene in questo caso, nel tempo, ma nel momento in cui non fosse più necessario la sua presenza perché la contaminazione non è più presente all'interno del sito, rimane semplicemente all'interno del sottosuolo con un terreno che presenta quindi, possiamo dire, un FOC maggiore rispetto a quello delle zone circostanti, però nulla di più e non c'è alcuna necessità di rimuoverlo. Un'altra domanda, sempre relativa alla gestione delle acque che sono state munte, chiede se l'acqua estratta sia stata prima raccolta in una vasca per separare la fase libera e poi mandata a trattamento, oppure se è stata mandata direttamente a trattamento. In realtà c'è stata proprio un'attività di rimozione del surnatante, quindi il surnatante è stato rimosso facendo degli scavi come delle piccole trincee ad hoc, mettendo la falda a giorno e quindi poi rimuovendo in modo localizzato il surnatante. Nel momento in cui è stato poi fatto il pompaggio non c'è più stata quindi necessità di fare una separazione acqua-olio all'interno dell'impianto. Guardo ancora un secondo le domande, magari ne faccio ancora una. Ecco, c'è una domanda in cui viene chiesto se per iniettare il PetroFix è necessario assolutamente utilizzare i pozzi. No, non è necessario usare i pozzi. Il PetroFix è un prodotto molto facile da utilizzare e diciamo flessibile, può essere applicato con diverse modalità, può essere applicato in direct push, quindi con iniezioni dirette, può essere applicato con postazioni valvolate, può essere applicato a spruzzo o con miscelazione con la benna sul fondo scavo. In questo caso è stata scelta la possibilità di utilizzare i pozzi perché era una soluzione che sembrava, e effettivamente si è rivelata tale, più facile da gestire nel breve periodo. Perché? Perché nel momento in cui io ho realizzato tutti i pozzi posso anche iniettare su più postazioni in contemporanea. Inoltre, tenendo conto che questo è un intervento di messa in sicurezza, il fatto di avere delle predisposizioni già in campo, eventualmente per il futuro fosse stato necessario correggere l'intervento, questo è stato considerato un vantaggio, quindi è stata scelta questa opzione per questo motivo. Temo che sia diventato tardi ormai, direi che ci sono ancora tantissime domande, quindi mi riservo poi di rispondere, come dicevo io, o tramite i due relatori. Spero che la presentazione sia stata di vostro interesse e per qualsiasi altra domanda i contatti di Regenesis di sicuro li avete. Qui vedete i contatti di Ondrej nel caso in cui vi interessi qualche cosa di particolarmente specifico, e vi ringrazio ancora per l'attenzione.